Okay, so in chapter 9 today in pre-algebra, we're in section 3, reflections in the coordinate plane. What type of first of all, you just told me a synonym for the word transformation. And you remember what that was? Ready? Transformations are change. So we know there is some math operation that is changing the location of every single point from an original to the image of the original. Yesterday, the transformation, yesterday was translation, okay? And one word synonym for translation is a no?
Image.
A translation is a slide. So in the word translation, we have the SL, slide. Okay, so those figures, you just told me we add or subtract to their points to get the new location. Today, we're talking about reflections. Where do most people see their reflections? Every day. In a mirror. So one other way we could describe reflection is say we're having a mirror image. A mirror image. Mirror images are interesting. Have you ever seen this before?
Yes.
What is interesting about this ambulance here? Gabe? The writing's backwards. So when you look straight at the front of many ambulances, that is what you see. Why in the world do they do that? Why would they have this backwards thing there? Jake?
This would be looking over in the mirror, you can see it.
Exactly, and you're not even a driver, so who knew that? Who knew that already? Is it because you saw that word and thought that's really strange? And then somebody explained it to you? Who had it explained to you? Has any one of you looked in a rearview mirror at that very thing, that word ambulance? Okay, so you see the reflection comes to you in such a way that you can read the word perfectly. When you look in the mirror, the word is ambulance. And so why would they want that to happen for this? Emily?
Because drivers don't like turn their head around, so they just look in the rearview mirror so then they can see that it says ambulance.
Right.
So they can like move.
So it's just one more way that they can get your attention that there's something important behind you in case you need to move out of their way, right? They're trying to get to the scene to help somebody quickly. And so when you're looking, drivers do sometimes turn their heads around. We have to, but more likely we'll be looking in our rearview mirrors a lot and you'll see that word. You won't even have to think twice that it's spelled correctly. Isn't that interesting? If you see that in your rearview mirror, you don't say, oh wow, that word is spelled correctly, and most of them are not. You know, you just read it and you say ambulance, wow, what do? I get out of the way. Especially because I probably see lights and a siren, I hear a siren. Okay? Helen?
No.
Okay, so let's see if we can identify reflections first before we get into the math behind the reflection. So look at these first two figures. Yes, you're going to have to draw them. Let me pause this. So when we reflect a figure across a line, we could place a line, somewhere between two figures. Why am I not? I'm frozen. There we go. We could take an imaginary line, right, and place it across and say, do those two figures look like they're reflecting across this line?
Yes. Yeah.
So what would prove that they are reflecting across this line, right?
You could take it, put it on top of it again.
Okay, so he's showing us that you could fold. Imagine that this was a piece of paper. You could fold it on the line, and if everything is lined up properly, right, then the figure on the left side would land right on top of the figure on the right side. So this is called, a reflection across a line. It's true. This is a mirror image across a line of reflection. Could we place a line of reflection in the second two figures here?
No.
So, if we took this very line, let me see if I can drag it over, and let me see if I rotate it. Will let me rotate? Usually it does. Let's see. we go. Okay, I think I have this almost positioned in such a way, imagine putting it there. Could this be a line of reflection for these two figures?
Yes.
I hear yes. Who says yes? Who says no? Why are you saying no, Ryan? Do you hear that? So if you fold it on this line, will we have this top triangle landing right on top of the lower one? Exactly corresponding, no. So there is no reflection across a line in this case. Do these look like little clone triangles though? They do, but it doesn't mean that they are mirror images. Something else has happened. Can anybody describe what might have happened if we started, let's say, at this, say this was the original one, and we ended up here? What kind of transformation might that be?
Translation.
Well, so if I just slide, do I end up there? No? So what else could it be, Olivia? A rotation, she says. Very good. So imagine I rotate it around. Could I get onto that place? A rotation, and then maybe a combination of a rotation and a slide. See that? Good, that's excellent. We're not going to do that, but you will do that in geometry. We're not going to do that. We may have a little taste of it, but nothing in depth in this year. Okay? Okay, let's see about the math behind a reflection now. Okay, so we want to, somebody is trying to guess the math behind this. So Ryan told us that if we folded this, if it was a piece of paper, we could land this, what is this figure called? Looks like a trapezoid on top of the other one, okay? And so what would be the math behind it? I mean, let's take a look at the vertices. This vertex up here and this vertex up here, what do they have in common with the line? Do you see it, Colin?
They are both the same angles. And,
Okay, but I'm just talking about their location compared to this line here. Yes?
They are equally apart from each other.
Do they look like they're both equidistant from that line?
Yes.
Yes, but this one's on the right side. Imagine a coordinate plane. This one's on the positive side. This one's on the negative side, okay? So otherwise, it feels like it's in the same location, right? Just the opposite side. So what might the opposite, if this was the y-axis, let's say this is the y-axis, and the very base, let's say, is on the x-axis. Try to stay focused here. I know there's activity going on. Let's say this is the x and y axis right here. Could anybody give me an estimate of this vertex up here? Where would that be? Ryan.
Maybe like 5.
So walk 5 and fly what?
6.
Okay, we could say that it looks like that's at least possible. They're both positive, right? Walk 5 and fly 6. So if we were going to get to this point, how would it compare to that other one? We would do what instead, Audrey? We would walk -5, and then where would we fly? 6. So what's the only thing different here? X becomes its opposite. How do you take a number and turn it to its opposite? What is the math behind that? Gabe? You would add a negative sign, but we need to have some operation. Is that addition, subtraction, multiplication, division?
You would multiply by negative.
That's it. You multiply by a negative. Multiply by -1. That's it. And that's the math behind this type of transformation. That's a reflection. So each point in a reflection is the same distance from the line as its corresponding point in the original figure. So we just saw a reflection in the y-axis gives you an opposite x or an opposite y. We just reflected this across this imaginary y-axis. And when we reflect it across the y-axis, do we have an opposite x or an opposite y? Opposite x. Do you see that? That's kind of opposite what somebody might have thought. We multiply the x coordinate by -1. Oops, let me see if I can cover some. So if we take a point at -10, 0. So we walk -10 and fly 0. Place it on there. and we want to reflect that point across the y-axis, we multiply x coordinate by -1. And what do we get? Stuart.
You get 10.
Good, so k prime, or the reflected point, is at 10, 0. So we're going to walk now 10 in the positive direction, and the y value didn't change at all. There's the reflected image of the original. Okay? Did that reflect across the y-axis? Did it jump across the y? Look at that. It went from here, and it went across to here. What axis did it cross? X? Really? What am I crossing when I move here? I'm crossing the y-axis, right? It's still sitting on the x. It didn't move away from it. Okay, so let's think about what would happen if we reflect in the x-axis. Let's start with a point at 3, 2. 3, 2. This is point P. You can probably be more precise on paper than up here sometimes, huh? So if I'm going to reflect that in the x-axis, and it's at 3, 2. There's the original at 3, 2. That means I want to jump it across the x-axis, right? So now where will it go? What would be the reflected across the x-axis location? Can you plot it? Where would it go? Colin?
It would go 3 and -2.
3 and -2. Let's see. 1, 2, 3, and down. P prime. So which value did you change now?
I changed the x-axis.
The y. So to jump over the x-axis, we actually changed the y value by multiplying it -1. 2 times -1 is -2. So when you want to reflect across the x-axis, take the opposite y. When you want to reflect across the y-axis, take the opposite x. Emily. If the point K, the original K point here, was reflected across the x-axis, which value are we supposed to multiply when we're reflecting across the x-axis?
0.
We're supposed to multiply the y value. So what is 0 times -1?
0.
It doesn't change it, does it? So this point K, if I reflected it in the y-axis, stays right where it is. And sometimes that happens with our transformations. A point may stay there. Okay, so that's kind of an exception that Emily just brought up. Good for you. Okay, let's try finding the original, plot the original, and then reflect this figure in the y-axis. So show your coordinates here and show both your original and your image. Whoopsie, you can't see what I'm looking at. There you go. Here. Okay, can you see now? You're going to plot this original and reflect it in the y-axis. Okay, so we have the original graph, and now we just need to find the reflected point, the reflected corners, right, the vertices. And so, if we're going to reflect in the y-axis, which of these numbers, which of the ordered pair are we going to change to the opposite? The x or the y? X. So what's the opposite of 0? 0 times -1 is 0. So that one didn't change, did it? And what is K? K, our new location for K is 0, 4. And our new location for L, now we can see some changes, is -5, 4. And our new location for M is 1. Okay, I'm going to make the new figure red. Okay, I guess I didn't put all the primes here. New location, I'm going to label them as well in a different color. You might want to do that in your notes so it looks different. The image is different, right? So when we find J prime, it's at the same location. When we find K prime, it's at the same location too. But now when we find L prime, we're going to walk 1, 2, 3, 4, 5 in the negative direction and fly forward. And M prime, same thing, we're walking in the negative direction but flying 1. Right? And when we connect these vertices, we can get all these other points. And is this a reflection in the y-axis?
Yes.
Yes, it is. You see it crossed over the y-axis. And that was by changing the x values. Okay, good. And now let's try it again, this time with a triangle across the x-axis. So all of our y values were multiplied by -1. And does this look like a reflection in the x-axis? Does it look like that? Crossing over the x-axis. We could fold it right on the x-axis and it would land, one triangle would land right on its corresponding triangle. Okay? The final question you might see in your assignment today has to do with lines of symmetry. And we have said that a line of symmetry divides a figure into two congruent images of each other. We could fold it on each other, right? So the question is, how many lines of symmetry does a square have? This should be a square. How many lines of symmetry? And tell me, where could I draw a line across this figure where it could fold right on top of itself? Where could I do that? Gavin, give me one line.
Right down the middle.
Okay, so he says like a vertical right here. That would work? Okay, give me another line, Caitlin. Okay, so she's describing a horizontal. There's another line of symmetry. And we need another one, I think. Olivia. Good, a diagonal, which means we could, if we could do it this way, this is not perfect, we could also do it this way. So is there any other way we could fold this figure onto its corresponding parts? For a square? That's probably it. So how many lines did we draw?
6.
Let's see. 1, 2, 3, 4. There are 4 lines of symmetry. How about in this? It looks almost like a rhombus shape. How many lines of symmetry do you think? Here, who could give us something? Izzy, do you think there's any line of symmetry we could draw there? He says straight down again. There's 1. And where else, Spencer? Okay, across, there's 2. And is there another way we could fold it right on itself, Brian?
Like change it to like a parallelogram and write it through the middle.
Okay, who thinks that this could be also a line of symmetry? Anybody agree with that one? I see some hands up. Imagine folding it. Would this vertex up here land on its corresponding? No, so that really isn't going to work in this case, is it? Because of the way these angles are. So it looks like there's how many lines of symmetry here? 2. Be really careful that you can fold it across your line and it lands on itself. That's the key there, okay? And there you go.